Hey everyone, I'm Vincent, and for this spot, I would like to share with you a project I've done last year as a student in applied math with Adnan at Central Supélec about the prediction of water consumption at the fountain of a solar pump. I would like to split this presentation into three parts. First, the project overview. Second, let's deep dive into the more prediction models, and third part about the conclusion. About the project overview. We basically based our study on the same system like many of the presentation of this summit. We use the data from GOGMA, and we would like to predict the collected water flow rate of the pump in GOGMA. It was pretty exciting to work on this kind of data as a data scientist and to have a real impact, try to have a real impact. We used two types of data sets. First of all, the data collected in GOGMA with the data logger, and second one, the meteorological data. It's an open source dataset by MinParisTech. It's called SODA and it's on our basis. It was enough for our study because we would like to predict the volume on the next 24 hours on an hour basis. We have many goals. Predict the collected flow rate every hour. It was basically the first step to do preventive maintenance. Predict the volume of water consumed each day. Basically, this one is to evaluate the backfill pressure on the ground and to reduce it, to help people to reduce it in case of lack of water in it. And the third one was to predict the maximum daily intensity of collected flow rate. This one was to reduce the maximum, so the queue in front of the dispenser, by helping people to basically a bit making the curve homogeneous. For these three models, we built three different metrics: the mean average error, the integral of the relative mean average error, and the maximum of the relative mean average errors. Let's talk a bit about our models. We created three of them. I will present you three of them. First two statistical models. First of all, the mean. It's a really simple model. For this one, we basically test the last 15 days, each hour. We do the mean on each hour from each day, and we predict the next day. This one was pretty good, but with this one, we can predict the small variation of each day based on the weather or that kind of causes. So we moved to a second one, which was the old winter model. This one is mainly using the literature to predict seasonal time series. In fact, our time series was daily seasonal, have a daily seasonality, and also might have a yearly seasonality. This model was working well, but we tried a different approach based on deep learning. For that model, we created honestly a bunch of them, many of deep learning models. But I would like only to present you the best one, which was the encoder-decoder model. It's based on a natural language processing approach using gated recurrent unit. It's basically some neural network. And with that one, we have better managed to predict the small variation. It was good, but overall, in the day, it wasn't that good. The small variation was good, but not all of them. About the conclusion, unexpectedly, it was the mean model which was the best, and that means that a bunch of our work was totally kind of useless. But if I have to rebuild the project, I might probably reduce the seasonality by subtract the mean model on the data set, on the consumed data flow rate on each day, and basically after that use the old winter model and the deep learning models to forecast or to predict the next day. It might reduce the noise for this model and they might be better, but we don't know. This project opened a bunch of perspectives. I will not share with you all of them, but basically, as I present in the goal, it helped mainly to probably do predictive maintenance or to reduce the backfill pressure. Thank you for your attention.